Hello everyone, my name is Hyugi Soon. This is my final year project presentation video, and the title for my final year project is Detection of Advanced Persistent Threat using ANFIS and Correlation Analysis. So this is the structure of the presentation. There are 9 parts to it. So this is the problem background. What is APT? APT is actually a sophisticated sustained cyber attack where the intruder establishes an undetected presence in the network and to steal data over a prolonged time. So they are called advanced because they use sophisticated tool. They are persistent because they stay in the system for a long time. So what is the goal of APT here? The goal of APT is to spy on the target or to steal the data from them. The characteristic of APT is that it has its own attack sequence. It has attack stages, stage 1, 2, and 3 and following, and it has a low and slow network characteristics. So this is cyber kill chain. Cyber kill chain is a model to describe the APT. So what it tells us is that there are the 7 stages of APT as described by CKC or the cyber kill chain. What it tells us is that when we break the chain, break the APT in one of the stages, the rest of the stages would not be able to continue. So this is what cyber kill chain tells us, that if we are able to stop the attack on one chain, one stages, we're able to break the chain. So what is a problem in current APT detection solution? Is that most of them experience a single point of failure where they focus on detecting one stages of APT, and once they fail to detect the particular stages, they won't be able to catch the APT. So our solution is to build a detection system that can detect all APT stages identifiable through the network traffic. This is the 3 stages that we are focusing on: delivery, C2C, and exfiltration. The second problem is that with the many stages of APT, most solutions nowadays, they do not correlate the stages. They do not the advantage of correlating the stages, and so here we are building a correlation module that can correlate the results of the APT stages that is being classified. So the aim is to develop a APT detection system using ANFIS, Adaptive Neural Fuzzy Inference System, to detect APT stages from network traffic, and a rule-based correlation module to correlate the stages into one APT attack scenario. So these are the 3 objectives: develop the ANFIS, develop the rule-based correlation module, and to test the performance of the system. And we are comparing it with Garfield's ML-APT system because we are basing the same data set that Garfield used. So this is the scope. We'll be using Garfield's data set. We'll be using Adaptive Neural Fuzzy built in Python and also MATLAB. And the 3 stages that we are focusing on: the delivery, C2C, and exfiltration. And lastly, we are comparing it with Garfield's result. So our proposed solution can be understood in 3 parts or 3 phases. Phase 1 is the detection system itself, where we train the ANFIS to classify these 3 stages, and then with the classified APT stages data, we are able to correlate them with the rule-based correlation, focusing on these 3 stages. And then we have the stage 3 where we measure the performance. So the methodology part. So this is the things that we'll go through for these 3 stages. The data preparation part. This is the flow chart. We transform the APT stages, which I'll explain more later on, encode the stage, split the IP address, and also train, test, split, and normalize the data. Feature selection, we did univariate selection, feature importance, and also heat map correlation to select our feature. So what is ANFIS? ANFIS is a fuzzy inference system trained with neural network. So the FIS offers us the fuzzy logic, the neural network offers us the learning capability. And here, this is an example of FIS. We have the falsification entry point we have the knowledge base that helps the system to make decision, the rules specifically, and then with the decision it makes, we specify the value to get us the output value. So this is a example of how the FIS works. We have the accuracy input and the answer time input, and it gives us the difficulty output. If specified, it gives us the inference based on the value that the specified value. It composes the value and it gives us the value of 0.57 difficulty. This is a FIS in a neural network architecture. We have the first input and second input. We have the membership function, the rule, the normalization part, and then we have the output membership function, and then it gives us a single output here. So phase 1 of the methodology part, we have the training data set. We feed into the fuzzy C-means clustering method to generate the initial fuzzy inference system with membership function and rules. This is not trained, then we will train this FIS with the neural network. This is done in MATLAB. Phase 2, we have the correlation part, where we correlate the outputs of a phase 1 dataset with infer stages, perform the correlation, and then we categorize it to full or sub-APT and visualize it. This is the third part of the testing, which we will see more later. The design implementation part, this is the original data of Garfield's. The feature selection part, this is the univariate selection. Here we see that destination IP and destination port is the features that we will want to include. This is the results of feature importance and correlation heat map. So the result is that we selected these 4 features to use to be trained. So which is these 4 columns here. So this is the data transformation that I mentioned earlier. Garfield's APT stages is there's 5 actually, and we are basing it with our CKC model. That's why we are transforming it to feed our CKC, the 3 phases here. The C2C, assess, strengthening lateral movement, and also internal recon are combined into S2. And then we did some engineering to the source IP here by splitting the source IP by subnet. Label encoding, train test split, data normalization, and this is the result of our training data set. 10 inputs that is normalized, and also 1 step output APT stages that we are aiming to classify. So this is the same thing mentioned earlier about the initial fuzzy inference system, and our training starts from epoch 5, increased by 5 up to 80. This is the rule, correlation rules that we have. This rule basically tells us that if the host is the same, or basically the source IP is the same, and this same source IP have all 3 APT stages being detected, 1, 2, and 3, you will have a correlation index of 2, and it's a full APT. If the same host has 1 or 2 APT stages, classified as sub-APT. So this is the implementation flowchart when we do the coding. And the phase 3, this is the testing, the metrics that we will use to test our performance, which we will explain more in the result section. So this is the result. So this is the result of phase 1. 10 inputs and 1 output. This is the ANFIS architecture of extracted from the MATLAB. 10 inputs, the input membership function, the rules, the output membership function that combines and composes to give us 1 output here. There is 133 rules here that maps to each membership function. So this is an example of the rules that we have, 133 rules that is trained to classify the APT stages. So this is phase 2, the development of rule-based correlation module. So once the APT stages is being classified and inferred, so the output of the MATLAB is being used to visualize. So here we have the original full APT attack timeline. Original means that it's based on the original Garfield's data. So this is not produced by our ANFIS detection system. This is what the original dataset have. We have the x-axis and the y-axis here, the timestamp and the step. Here we have 35 full APT attacks performed by 35 different infected hosts. And we can see here, one example is step 1, 2 and 3 here. So this is the infer full APT attack timeline. This is produced by our ANFIS detection system based on the same dataset earlier. So this is what we get, and this is what it actually looks like. So 15 full APT attacks are being inferred or classified by our detection system. There is 10 that is correct, there is 5 that is wrong. So the reason, or we want to analyze further, what is the potential reason that caused 25 of it that is not classified as full APT attack. It might be that one or more stages is being wrongly inferred. Remember that the correlation rule, that the same source IP with all 3 stages available classified is considered full APT. So what happens is that the ANFIS detection system wrongly classify one of the stages to others. So instead of 1, 2, 3, our ANFIS detection system might have classified as 1, 2, 2 or 1, 1, 2, so that instead of being a full APT attack, it's being classified as sub-APT attack instead. As to why the detection system have this wrongly classified, we'll further explore in the testing part. So this is the sub-APT attack. So before this, we were looking at the full APT. So here is the sub-APT, which means that it has 1 or 2 stages of APT only. So this is the original one. Again, it's based on the original actual Garfield's data. It's not by our trained ANFIS detection system. Here we see that there's 621 sub-APT attacks performed by different infected hosts. This is how the chart looks like. And this is the one that is classified or produced by our ANFIS detection system. So we're actually trying to match what we are able to classify and visualize to what does the actual graph looks like. So 641 sub-APT attacks are being inferred in this chart. Out of it, 428 are correct, and 213 is wrongly classified. And what is the potential reasons that we are looking for? Might be that the 213 that is wrongly inferred might be because 1 or more stages are being wrongly inferred, but they are still categorized as a sub-APT. So meaning that, for example, that a sub-APT might be step 1, 2, but our detection system classify as 2, 2. So even though it wrongly classified, is still a sub-APT here. As to why our detection system wrongly classified, we will also explore more in a testing of performance section. But one thing we can see is that S3 has lesser point compared to the original chart here. So one reason that we might be looking for is that why our detection system is not doing good in classifying S3. So this is the phase 3, the testing part of the performance. So this is the epoch chart. This is the epoch chart that records the train and test error. So the blue one is the train error and the red one is the test error. So we can see that the training error is decreasing gradually and stops at 45. After 45 is a plateau. The same as well for test error. But here we are looking at the fluctuating error here in the test error. And why does it increase while the train error decrease? Well, the reason might be because it overfitted the training data. So when the ANFIS is overfitted, it gets better at the classifying the train data, but it gets worse at classifying the test error. And the result that we are taking from here is that epoch 30 is the best epoch that we have, and so we are taking epoch 30 as our result here. So this is the same result, but this is in table form. So we have the test error of 0.23. Here we come to the confusion matrix. 3 stages against 3 stages. We are looking at the true label and the label that we classify into. And 2 things that we see is that, first of all, half of the S3 is being wrongly classified as S2. This is because S2 is being overfitted. What happens is when S2 is being overfitted, other stages are being classified as S2 as well when it is not. So this is what happened. Maybe one of the reasons that causes half of this S3 being classified as S2 instead. And the other thing we notice is that S2 has a high number of being classified as S3, which is wrong here. But we are seeing S2 have a high positive and also a high false positive here. This is a AOC ROC graph that we have. This is a true positive rate plotted against a false positive rate, and the information that we're looking at is the area under the graph or under the curve. So S1, 2 and 3, what we can see is S1 has a very high area closing to 1, which is very good at classifying S1. S2 is also okay, not too bad, but S3 has a not very favorable numbers here. The black line here is actually 0.5. Anything lesser than this black line, lesser than 0.5, does not have classifying capability. So we see that our S3 has an area of 0.59, which is not good. And this result in the low true positive for our full APT attack earlier. So if you remember, why is it that that is 25 that is not classified as full APT attack? Might be because our ANFIS detection system is not very good at classifying S3 correctly. So instead, it missed out one of the stages and it did not become a full APT. And here we come to the classifying reports that we have here. S1, S2 and S3. We see that S1 is performing very well with a precision and recall more than 90% and a low false positive rate here. But what we see in S2 is that we have high precision, high recall, but also high false positive rate of 28%, which is reflected in the confusion matrix earlier. But in S3, we are seeing a low number here, 48% and 29%, which is very low, and also false positive rate, which is quite low as well, which is good. So what contributes to the high false positive rate of our S2 here? As mentioned earlier, probably because it's being overfitted. That's why it has high true positive, but also high false positive here. Now, as to why S3 has low precision and recall, and also low AOC ROC as we see here, the potential reason might be because of the imbalanced data that we have. You can see here the support means refers to the number of data in our testing data set. S3 only have 177, which is the least among the data here. So this might contribute to the poorer learning result to classify S3. And lastly, we compare our result with Garfield's result. So Garfield's ML-APT has 4 APT steps, a true positive rate of 81.8% and a false positive rate of 4.5, and also accuracy of 84.8, which is comparatively higher than what we produce in this research. 77%, 18%, and 77% respectively. And to analyze this, we're looking for the reason why there is a lower accuracy than ML-APT. The potential reason might be because when we transform our stages, APT stages, from 6 APT stages to 3 that we are focusing here, some of the data characteristic might be mixed up or loose when we combine them together. So this might be one of the reasons. And the second reason might for the high false positive rate that we have for this detection system is because of the high FBR for S2, which I've explained in the previous slide here. So the findings and contributions. What findings do I have? The proposed solution, which is this ANFIS APT detection system, achieve accuracy of 77% with a true positive rate of 77% and a false positive rate of 18%. The trained ANFIS is capable of classifying S1, the delivery stage, very well, as we can see earlier, but we have problem classifying S2 and S3. The potential causes are that S2 is being overfitted to the training data, and also the imbalanced data set where S3 is lesser compared to S1 and S2. And lastly, the transformation of APT stages based on CKC might not be appropriate to Garfield's data set. Lastly, on our contribution is that we have produced a data set labeled with APT stages based on the CKC model. We have an ANFIS APT detection system that classify APT into its stages, the 3 stages, a correlation module that correlates the 3 stages and then visualize it to full and sub-APT attack timeline. And the cyber personnel can use this system to better pinpoint the APT attack period with the visualization that we have. And also, this reconstructed attack timeline also gives the cyber personnel insights into the attack stage of APT. Lastly, a suggestion for future work. Because the APT data is scarcely available in the public, we suggest that we should improve on the existing APT data set by adding network data from different network layers such as the transport layer and application layer. The second is that because Garfield's synthetic data now only consists of malicious data, so to better mimic the real environment, that we might be able to inject burnout traffic or normal traffic to form a low and slow pattern. And thirdly, more robust correlation rule when there is a bigger set of data feature available. And lastly, comparison of different classification techniques such as SVM, KNN, nearest neighbor, and also decision trees. Different classification technique might be used to actually identify and classify APT. That's all from me. Thank you.